This is the digital input for the QAM. It starts off by, once an enable bit goes high, it'll go through a already set preamble, which will allow for the output block to understand the values that it's getting. And so the preamble will go through a shift register that shifts by 2 bits each time. And that goes into a mux, which is controlled by a count compare block that will count up until the very end of the preamble. And once that switches, the mux will switch into the data in.
And then this block takes a 16-bit data and then stores it and then sends it 2 bits at a time through the mux, which is now set to 1, and then into this K-switch block. And then this K-switch block then switches it from binary to thermometer code, which then goes to the to this mux here.
And for this project, one thing we learned was Verilog.
This is the all-pass filter. The purpose of it is to make 4 different phases, which is part of the 4 QAM that we're creating. And so how I designed this is I cascaded 4 all-pass filters. The first one, we wanted the first phase to be 45 degrees. So the capacitor value I calculated using this equation, and I set all the R's equal to each other. So plugging in F, which is our operating frequency at 100K, and then R for 10K, and then plugging in 45, which is the phase that we want, I was able to determine that the capacitor value should be 65 pico. And then we wanted each phase to be 90 degrees off from the 45. So then these 3 all-pass filters are the same, and each one does a 90-degree phase shift off each one. And to do that, I'd use the same thing, but plugged in 90 degrees for this phase, and that is how the all-pass filter works. I learned that how to plot the AC phase in the Cadence analog and design environment. So when you go to that window, you go to results, and then there's a drop-down menu, and you click direct plot. And then after that, there's going to be another drop-down menu, and you can click AC phase. And then once you click that, it's going to bring up your schematic, and you press what wires you want to show, and then press escape, and you'll see the plot.
So these are the amplifiers. For the first amplifier going into the transmitter, I just made it a voltage follower because its input is already like rail to rail almost. So for this simulation, it didn't really make sense to actually amplify it, but I just put it there for completeness. And then there's not a great way to model a transmitter and receiver in Cadence, so I just put a voltage divider to simulate the attenuation, and that feeds into the receiver's amplifier, which is just a basic non-inverting amplifier. I wanted a gain of about 10, but with the non-idealities, it ended up being about 15 gain. And then with my simulation, the output is approximately the same as the input to the transmitter. It just has like a slight offset, but yeah. Something I learned is how to resize capacitors in Virtuoso. I didn't do it for this part, but I learned it while helping my teammates.
Alright, so this is a low-pass filter. I just use a simple RC network with a buffer on the output so that we don't have any additional impedance problems. I used the RNC values to get us a frequency a little bit higher than our desired 100K, so we don't risk attenuating our signal, but we also reduce the noise at higher frequencies. Learned is how to resize capacitor, because given the 1 picofarad, we needed 100 picofarad for this component, and so.
Hello everybody, today I did the ADC, and so how the ADC works is we start off with a 5-volt VCC because that's what our signal that's coming in is the maximum, what the maximum would be. And then I use 4 10K resistors to split it up into 4 different voltages, 3.25, 2.5, and 1.25. So it could characterize each input signal as above or below to give out bits, and then these bits will tell whether it's in the first category, second category, third category, or fourth category, which will eventually help us tell the phase of the signal. And then one thing I learned to do was how to simulate a VIN with different voltages so that I could see all the characteristics on one plot. And so I simulated from 0 volts to 5 volts over a certain time period. And so I can see each bit change as that threshold is passed.
Hi, my block is a phase detector. It's an XOR type phase detector. How it works is it takes 2 input signals, and whenever only one or the other is on, it outputs a high pulse. This is the complex CMOS gate version of the phase detector. And I learned how to go from schematic to layout and how to optimize the design there. That was my biggest takeaway.
This is the digital output block of the QAM. So we'll start by getting a preamble of data, and this will count until the preamble's finished. And so while we're still getting the preamble, we're going to be assigning bits based on what they should be versus what we're receiving, because they won't necessarily line up. And so we do this by compiling the entire preamble, sending it to this bit assigning block, which will then correspond the proper bits to each of the inputs of this selecting mux.
And then after that, this mux switches to a 1, and then it takes a 3-bit thermometer code from the ADC, and then converts it to binary. And then that binary goes into the mux select, which is then used to convert it to its correct value. And then that 2-bit number then goes into an add and shift and a shift register, which then makes it to a 16-bit string and then sends it to data out. From this block is how to make 10 test benches in Virtuoso.